This is going to be the last slide of chapter 3. So what is the analog Zeno effect? In the analog Zeno effect, we consider a differential equation like y prime of t equals f of y of t with initial condition, let's say y of 1 equal y0 for any fixed continuous function f from real to real. So this is going to be a one-dimensional differential equation, first order and autonomous, because f itself is not allowed to depend on time. This is no restriction, as we've seen before. We can always introduce another variable as parameter. Now let's call the solution of this differential equation y, and consider variant of this differential equation, a modified differential equation system z prime of t equals f of z of t times w. So we have a variable z instead of y. We have another variable w, it's a system, where w is supposed to solve another differential equation, w prime of t equals wt. So this is a system, first order, two-dimensional, still autonomous, and we're going to need two initial conditions. Z of 0 equals y0, and w of 0 equals 1. Why do we want to consider this modified differential equation? Because if we solve it, right, let's first solve this one. This is independent of z. This is dependent on z on w. This is independent, so we can solve it. We know the solution is the exponential function. Wt is exponential function because of this initial condition. And then it's easy to verify that the solution of this differential equation is the original solution composed with the exponential function. Actually, I want you to verify that. So we're going to take a quiz on that. But the gist is that we have now accelerated the solution. So that is the same basically as previous y, but with a modified differential equation, z evolves exponentially faster, right? It accelerates. That's why it's called analog Zeno effect. It's the fact that we can basically accelerate every autonomous ordinary differential equation to evolve exponentially faster. So your task, your homework is to verify that this is indeed a solution. And your task is also, that's a message. Differential equations can be accelerated, which has some consequences, which, for example, we cannot really define or consider time complexity for analog computers because it's, can always be accelerated. Which means if we want to define time complexity, which we do, then we need to be very careful. And here's a very good paper that introduces several non-naive notions of time complexity and proves them all equivalent. Your second homework is create a doubly exponential accelerating differential equation. So we've already accelerated once exponentially. Let's do it a second time. We can do it again. And again and again. I want you to do that. So that concludes what I've still owed you from chapter 2 on accelerating computation, accelerating analog computation. And now we're at the end of chapter 3, analog computing. We called basic calculus, derivative and Riemann integral and Stieltjes integral. We discussed differential equations, ordinary differential equations of several classes, first order, second order, and so on. Then we talked about engineering, namely Busch's differential analyzer with the 3 gates, the gear, the differential, and the integrator, ball disk integrator, and Shannon's mathematical theory of the differential analyzer, the so-called general purpose analog computer model, defined as the least class of function containing constant, the identity function, constant scaling, rational scaling, averaging, and Stieltjes integral. And then we discuss consequences of this, namely the fact that this class of functions is precisely the class of function solving differential algebraic equation systems. From this, we conclude that certain functions cannot be calculated by the differential analyzer, including Riemann zeta function and the gamma function. And finally, we ended with an analog version of the Zeno effect, accelerating computation, which means there's no, at least naive complexity theory. Defining complexity for analog computer is a difficult endeavor. So that concludes our chapter 3 on analog computing, and upcoming is chapter 4 on quantum computing. Thank you very much for your attention, and see you next time.